You there?
Yep.
Okay, so isomerism you've looked at a bit in organic chemistry, and it applies in the same way here. So there's two types, structural isomerism. Can you see the whole paper?
Yep.
Structural isomerism and stereoisomerism. Structural isomerism is about the connectivity of the atoms. So a pair of structural isomers could look like this. So that would be one isomer, propane, versus, actually propane is not a great example, I'll make it butane, versus another one. So if I put the CH3 group there, here we go, hopefully you can see what's going on. Methyl propane. So those are structural isomers because they're connected differently. Stereoisomers, different arrangement of atoms in space. And two types in space. Two types. First type is geometric isomerism. Can you still see it?
Yep.
Geometric isomerism.
Just that I can't.
Okay, that's right.
Is the writing supposed to be clear?
Yeah, ideally, is it not focused?
Okay.
Do your best, don't worry. Cis trans.
No,
So
it's
you've
clear.
seen. Okay, well, so you've seen this in organic chemistry as well. So that would be a trans isomer, whereas cis would have the methyl groups on the same side of the double bond. Now that applies the same way when you do transition metals. So imagine you've got a a square planar. So that's my metal ion in the middle. Imagine a square planar arrangement like this, square planar complex. This is cis because the two groups are on the same side. I could make it trans by switching a water and a CN. So that would be cis-trans isomerism that you see in square planar complexes. The other type is optical isomerism. So we saw this when we did organic chemistry, and you have four different groups. So you might have CH3, sorry that's 3, OH, H, C2H5. That would be a chiral compound, because if I draw a mirror image of it, the mirror image is not superimposable on it. So here we go, there's the OH, so I just draw it out like this, and those two would rotate plane polarized light in different directions. With our transition metal ones, it happens when you've got a bidentate ligand. So imagine your 1,2 ethane 1,2-diamine. Here we go. So CH2. It's bidentate. So let's draw the shape, but it's still octahedral. Here we go. So that would be. It's quite hard to draw. So I'm going to just draw them as actually propellers because I think that's a bit easier. But I can draw a mirror image like this. So same ideas like this. 3D structure. Instead, I've got those two joined together, those two and those two. So can you see those two? It's quite hard to visualize, but they're non-superimposable on each other. So they're stereoisomers, optical isomers. There's one other type actually while we're doing it. If we go back to cis-trans, you can also get this with octahedral complexes. So say you had the copper complex. Do you remember you had the one that had 4 NH3 and 2 water ligands? That would be cis because the two waters are next to each other, whereas this would be trans because the two waters are opposite each other. Hopefully that makes a bit more sense. Let me know if not. There's some good stuff in that chem sheets pack that I gave you, I think, on this. Okay, press stop.